Well, that might work. Everything is different on this silly thing. Okay, that worked. Okay, I don't have the projector going. Let's do that real quick. Okay, so I don't know what's going on as far as the speed or anything of anything. But we got one marker. It's not great. Okay, let me go see if I can steal a marker or two somewhere. Okay, well, it came up. Okay, so let's move on to one other thing. But before I do that, let's go to, there's a calendar up here. There it is. Okay, today is the highlighted day. So that shows that there's some stuff due tonight. I'm not sure what, we look back and see. I mean, I can move these down a little bit. And so what I'll do, the ones that were named quizzes, they may change their name. But if you already did them, it's okay. And so then I need to fill out something. There's one missing here. I don't know which class it is. The problem is when I see them, I see all of them. Let's see, that is statics. And that's this class. So apparently I don't have a fluids one for them. So I'll fix that in fluids. That's not a big deal to you guys. So there's one final thing in chapter 12. Okay. And it's this section right here. But it has that one, wait a minute, that one with it too. Let me see if I can get rid of that. So in this, the aspect ratio looks fine on this screen. I don't know about up there, but these are two square blocks, except if you look at it on this monitor. What you're going to do is you're going to try to relate the motion of block A to block B. However, they can be complicated like this one, or even more complicated. So there's videos in there, but I'm going to just go and do a particular problem so that, or I can go back and do that one right there. But you can read through and do that one. So I think I'm going to go ahead and I'm going to pick up a problem. Let's see, problems. Okay, so he starts with this 195, which maybe we'll just do that one, or maybe we'll do this one. I don't want to do the too complicated first. Let me find a simpler one. That actually has one rope, so let's just do that one. So these problems may seem like overly complex until you do like one or two things. Identify how many ropes you have. That's the first thing. The second thing was look at the length of each rope. And that's it. Now, it turns out you've got to have a datum, something, a fixed location. So you got to identify a datum. And so in this one, he's kind of already done that for you. In other words, he's basically told you this little part's attached to the wall. It's not going to move particularly anywhere. So I'm just going to pick this as one of the datums. And what he's drawn here is a little distance down to the pulley C, and then a distance down to the pulley B. Now, you can have a description from here to here, but whatever the motion of B is going to be the motion of this thing. So those things go together. Then he's done this. Now, see, I would not have done it from here. I would have done it from here to over to A. Now, it turns out it really doesn't matter that he and I disagree on this because the distance between here and here doesn't change. So if you do that, first thing I've identified is if I follow this rope, it goes over, up and around this C, and back attached to this B. So I've got one rope that's here, I'll just call it one. Then I got another rope that goes up and over the top of this and then spins onto this motor here. So that's going to be my rope 2. So I'll do a rope, maybe I can do on the right side of the board, I'll do rope 1, and over here I'll do rope 2. So if you look at the length of rope 2, length of rope 2, you just sort of lay them out. Well, what's the distance from here to here? Well, it's SC. And then there's this part right here. And this, in the book, he'll label that in red. I could have done it in green, because I have a green marker. But this little part here, even as this thing moves around, the distance from the top of that to here remains fixed. So generally, he'll use a capital delta. I just use a big delta. So I'll say all the deltas, and these are the fixed distances. Now, it'll become more apparent on the second, when we do rope 1 over here on the second part of this. And then I've got a distance that goes from here out to A, which I'll call SA. And then the rope that continues, like this rope, is not considered. So he's identified a location A, and so if we want to know the length from C up and around here to A, that's what we got. Now the next thing generally happens is they want to know the derivative, the time derivative. They'll want to know the time derivative of the length 2. How does the length of rope change as a function of time? Now, if it's not elastic, it doesn't bounce around, which is what you kind of assume, it basically is 0, which is basically L2 dot, or here, let me reverse those two. L2 dot is equal to SC dot plus delta S dot, and we have to remember this is fixed, plus SA dot. If you think about this motor's turning and it's apparently pulling the rope that way, then point A is going to be moving to the right. So this distance is going to be increasing. So this is going to change with respect to time. So is that one, it's going to, if it's pulling to the right, it's going to get shorter. So the fact of the matter, all you have to identify is that they do change with respect to time. So what you get is this, and I'll go ahead and put this in as 0. You get an equation that relates the velocity, velocity of C to the velocity of A. Now, let me let's see. We hit one point down, and that is direction. Okay, since this vector points from a datum to here, then the velocity will go in the direction of that. So now the velocity of C, a positive velocity of C. Here, let me try to see if I can move it to let's see, move it over here. And I'll say it like this, S dot C. So the S dot C is positive down. And as well, S double dot C. And what we'll do here is, since the velocity, or since the position points to the right, then SA dot and SA double dot are positive to the right as well. I'll go ahead and erase those in a minute, but that's important to recognize, and it'll become more important in a second or so. So all I get here for the length of 2 is a relationship between this point and that point. That's all I get. So it's pretty boring as far as this one goes. But for 1, it's a little bit, I don't want to say it's exciting anyway, but for 1, it's a little bit different. So first of all, let me go ahead and use the green marker. The green marker, basically, this distance right here is part of the delta. This distance right here is part of the delta. This distance right here is part of the delta. And if you trace this rope, it basically starts here, goes all the way up until it ends right there. So if I just look at the length of rope 1 equal to, now what I'll do is I'll do this, all the green lengths are added up, plus, okay, the distance from here to this point is SB. Now, I gotta look at this one. The distance between here and here If you look at it from this point, it's SB minus SC. And that's that distance. But there are two of them, this one and that one. And it's pretty much that simple. Two of them, and then SB minus SC. And there's nothing else there. So the length is just all the greens plus this section of rope plus these two sections, and that's it. So then you just go in and take the time derivative of it, and plus 2 SB minus SC, and what you get is this one will give you 0, that one will give you 0, plus SB dot plus 2 SB dot minus SC. That's it. So, what this does, what this is a relation between the B and the C. And essentially, the only two movable parts of this, the pulleys there. So how do you get this? Okay. Well, let's now, I mean, I don't know what his question is, but I'm going to ask several questions. Let's say A moved to the right, or let's start with the simplest one. Velocity of A up there that he has right here is equal to 10. What's the velocity of B? I mean, you could ask what the velocity of C is or something else, but the B is the thing that you're most interested in. So, as this thing is drawing it on there, then this tells you, because of this tells you that SA dot is equal to 10. It's moving this direction, it's the same as that. So you could put this in as 10. Then from here you can get SC dot equal minus 10, because that would be positive 10 and move to the other side. Then you could take this, and I guess let me write one more step here. First of all, here, hang on. You got two of those, so let me finish this part out, because then it'll make things a little simpler. Okay, so I got SB, 1 SB, 2 SB, 0 equal to 3 SB dot, 2 of those and 2 of those, minus 2 SB, SC, or, well, I'll go ahead and do. And then I could say 3 SB dot is equal to 2 SC dot. So now that I've got minus 10, I could put in minus 10 here and have minus 20. So in other words, I took this over to here, open up over to here, and put in a minus 10 into here, you got a minus 20. And then I get this, and I could divide it by 3, and I'd get SB dot equal to whatever that is, 20/3. But the reason it's an odd number is because as this pulls up, you know, the extra ropes here, the pulleys actually move it, and that's the reason you have this, in other words, is you have pulleys, because you, first of all, you can have we're looking at positions, velocities and accelerations, but if you're able to provide a certain amount of torque here, that torque would translate into a tension here, and whatever that tension is, say 100 pounds, I mean, I'm just making stuff up, say it's 100 pounds, well, this gets distributed across here, and you got 3 of these. So if you did a free body diagram, and this is 100 pounds, you're looking at 2 of those making up that would be 50/50 and 100. So it'd be 50/50, and then another 50, because this is the same rope, so you're talking about 150 pounds. So you're able to pull a tension, but actually pick up more weight with that. But it becomes a little slower. I don't know what 20/3 is. Just Let me just check real quick. I mean, it's not that big of a deal. About 6.66. I didn't put a unit on it, but so let's just say it's feet per second. So let's say you were pulling at 100 pounds. Now, you know, this was pulling at 100, this is now 150. You're able to pick up a larger weight, but it's going slower. And so it has a minus sign associated with it. And the reason being is because positive for SB is down. So the actual velocity of this thing is going up. And that's all there is to it. Just if you identify how many ropes you have, and you have to write the length equation for each rope. You got to you don't actually have to write this down, but it is a good idea to include it because, just self-recognition that there are parts of the pulley that are not going to change their length. These will, and then once you get this, you can do this in both ropes, and then when you get done, you can kind of figure out how to put them together. So this is what you do if someone gives you the velocity. They can give you the acceleration. You can do the same exact thing. You just take two derivatives, and then the flow of the work becomes the same. What happens if somebody told you that A moved, here, let's separate those. Point A moved to the right 1 foot. How far does B move? And in a minute, we'll go back and see what question he actually asked. Okay, so if A moved to the right 1 foot, or to make my life easier, well, yeah, I'll just say 1 foot. Move to the right, how far does B move? He didn't tell you how long it took A to move. So, in my mind, I'll just say it took 1 second. If it took 1 second for A to move to the right 1 foot in 1 second, then the velocity would just be equal to, or here, I'll just write it down that way. SA would just be equal to 1 over 1, or 1. Now, SA dot, in other words, would be just 1. If that's the case, then if during that same 1 second, you can figure out how far B moved. And what you would do is just say, well, SA is 1. You'd go back over here, and instead of putting in this, you would, take your SA, wait a minute. You took your SA, that sounds weird. You take your SA, and you take your SC dot equal to -1 because of this, and then you took it over minus 2 times 1 over 3, or minus 2/3. And this is SB. Now what happened here is during that same 1 second that A moved to the right, during that same 1 second, B moved up, moved in that direction, 2/3. So it didn't move as far. So in order to get this to move a longer distance, you have to pull it further, and this moves slower and moves a shorter distance. So in the text, he will have a strange way of working these problems that is okay for the distances. You have to think once or twice. I think what he was doing back last time I looked, he would take the two states at the 2 and subtract them. To me, that's obtuse in a way, so I would just assume that everything happens in 1 second. So if he said A moves to the right 10, then I would say it moved 10 feet, and this would be 10. It would still move in that 1 second, and this would be 10, a minus 10. You'd put it over, and you'd get back. Did I copy that over wrong? I think I copied that over wrong, didn't I? In the first part? I think I did. No, I didn't. No, that was right. I multiplied the 2 times the 10 and just wrote it down. That's right. So if it moved 10 feet, then SA, you could say, okay, I'm going to assume it happened in 1 second, and you'd say 10 over 1. You would take your 10, you would take this equation and find the SC. You would move it across over here, and then you would find your SB. And then you would figure out that if A moved to the right 10, then this moved up 6.66 feet. And so, and that's pretty much all these problems are. Identifying the ropes. Actually, this one probably should be in right there. It should be identify a datum, do the length for each rope, and then work it out from there. So yeah, I guess you really probably, you have to do your datum before you write down the equation for each rope. Let's see what actually he asked on this one. Okay, determine the speed of B if A is moving downward. Wait a minute. Is that the, oh, that's 205. Okay. Determine the time needed for the load, 203. For the load at B to obtain the speed starting from rest if the cable is drawn with an acceleration. Oh, okay. That's a good one. Okay. Let's, since I'm going to have to scroll it back up, let me go ahead. I've got the equations already worked out here. I'm going to write a couple things down there. So he wants to know the time needed for B, the velocity of B, to equal 10 meters per second, starting from rest, velocity B 0, the same thing, velocity A 0, equals to 0. If the cable is drawn with an acceleration, okay, the acceleration of the cable it's drawn into the motor with an acceleration of 3 meters per second squared. So let me scroll it back up and put the drawing back on top of this, and I think we can work this part out. There we go. So, ironically, there's nothing really new as far as developing the rope equation. In fact, we've already done that. I can erase the confusion around everything and basically come down to this equation for the rope that I identified as 2. And I can do this one more. SC dot 0 equals SC dot plus SA dot. I can also take another derivative. Okay, so I'll do that same thing over there. And what I'll do is I'm working that one problem. Oops. So I want to keep this and get rid of all that. Now, I can take a derivative here again. Now that you've got 2 derivatives, you're starting to deal with the acceleration. So he says the acceleration to the right, the acceleration here, is equal to 3 meters per second. So that is SA. So this means SA double dot is equal to 3 because it's going to the right, the vector's going to the right. He said it's pulling into the motor with that acceleration. Therefore, I can put that right here and say SC is double dot is equal to -3. Then I can take this and put this in here. This is -3 times 2 is equal to 3 SB double dot. So now the 3 cancels this 3, and SB double dot is equal to -2. So now that I got -2, what that means, okay, here. So let's identify the positive. This is SB positive. So I'll say this is a positive SB. This is a positive SB double dot. The fact that that's negative means it's going up. Now, the thing starts, it has a constant acceleration. It starts with everything dead still. So if I wanted to write an equation, it would look a lot like this. If it's constant, that's what it looks like. If this thing, well now, he wasn't interested in the position, he was interested in the velocity, that's right. So the velocity equation becomes v naught plus acceleration of t. So this is the standard form for constant accelerations. Hang on. So the constant accelerations look like this. Actually, we don't even need this one. This is the only one we need. He wants to know how long it takes for this to make 10 meters per second if the initial velocity is that and the acceleration is now. Here's the thing. I know it's 2. The sign just tells me it's up. I don't really care about the direction per se. He just says the velocity. So I'll put a minus here, and -2, which I said 2, and I wrote 3. 2t, so t is just 5 seconds. So it took 5 seconds for that to happen. So anytime you see the writing in there where it says it's constant acceleration, your mind should immediately go back to these 2 sets of equations and say, okay, somehow I've got to use those. So these are there, they were there earlier, but they continue to stay there. And that's pretty much it. So he could have asked another question like, how far did it move? And if he asked that question, it'd take 5 seconds. You go back and put it in here. How far did it move in that 5 seconds? Well, S minus S naught, move that over, is equal to V naught T plus, and that's still my 2, so hang on, minus 2. Now it's 5 seconds squared over 2. That's 0. So it moved 25, the 2 and 2, so it moved 25 meters in the process of accelerating up to 10. So 5 seconds it covers. That's got to be some pretty long cables there. But he didn't ask that question. But he could have. You know, how long did it take? That would have been an interesting question, but nothing that more difficult. He could have said, how long did it take and how far did it cover? And you would use this equation to figure out how long it took, use that one to figure out how far it covered. That's pretty much it. Let's just look at one other maybe an interesting one, is you just go throughout. Some of them are more interesting, but first thing is identifying here. I see 2 cables here. Here I see it goes around, around, and back, and around. I see one cable. Let's just do that one. There's a lot of different loops there. Determine the speed of block B. Okay, so let me get all this stuff off of all the extra writing off. And block B, this block over here. So your first thing, well, first we've identified I only have one row, so I don't really care. But I gotta find a datum, something that does not move. I could pick this spot, it doesn't move, or this spot. I think I like this one a little bit better. So now I'm gonna, seems weird. He labeled A and B, but he didn't label C or D or E. For that matter, let's be really specific, okay? And I'm gonna be like way down to the nitty gritty here. So I'm gonna basically, let me zoom this in so the picture is not so small, because there's not much information I need, okay? That may be, no, that's good. So I'm gonna identify all of these locations. I'll show you something interesting. He's already said A, he's already said B. So I'm gonna use C, I'm gonna use D, I'm gonna use E, I'm gonna use F, I'm gonna use G. Now, you don't need to do all those, but here's one of the things you know. The distance C and D remains fixed. D and E remains fixed. And F and G remains fixed. So let's just go ahead and do this. Okay, now this is gonna be my datum for everything. For all of them. So, here we go. I'm gonna just go SD, I'm gonna go SE. Now you already know distance between C, okay, so when I'm saying this, okay, so SC always equals 0. The distance to C, that's always 0. But these are different. And this one goes to SF, that point. So this is supposed to go here, 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 and here. SG. Am I getting close to the end? So all you do is you just write the length of the rope. Well, first thing, I'm just going to say the length of the rope is I'm just going to put in all the deltas. And I'm going to say, okay, oh, I've got one more to do, and that's to here. Okay, the length of the rope is SA. I follow the rope, and then I go to here to here. That would be SG. Then I go from here to here. Well, that is SG minus SD. I'm kind of running out of room. SG minus SD. That covered me back to here. Then I come to here, SD minus SF minus SD. Okay, that got me to here. And then SF, this part from here, SF to SE. SF minus SE. Now, it's a lot of stuff. And what I will do now is I can go in here and identify a couple of distances that remain fixed and possibly move them over here. Now this is, if you get too much into this, you can find out that there's a lot of, you can make it complex, which I've done here. But this distance, SE minus SD, is fixed. This distance SD minus SC is fixed, as well as SG minus SF is fixed. So at this point, I'm just going to take some derivatives, and then I'm going to move things apart, or maybe I should put them up there. This derivative, okay, so let's do this. Okay. Now, let's go ahead and write these over there and recognize that this one is 6, so I'm just going to put this one in. Here we go. This one is 6, or SA dot, SG dot, well, plus SG dot. Now, you got another SG, so I'm going to go ahead and do this. But here's the thing about this. Since these two are connected, SF dot is equal to SG dot. So in other words, these are two that are moving rigidly to the right. So everywhere I see a SF dot, here and here, I can change that to SG dot. So what I'll do is I'll kind of copy this down. The other thing is, what is SD? SD dot and SE dot. If SC dot is SD dot, sounds weird, SE dot, all equals 0. These 2 points are not moving. So I hate to monkey with what I've written here, but I'll go ahead and do that. Gone, gone, and gone. Now, those are gone. Everywhere I see an F, I can put a G. So I got 1, I got 2, I got 3, I got 4, I got 4. So I could move this to the left and put a 4 there. And then that's on the left-hand side, so I guess I could do this. And that's it. Now, there should be something kind of familiar. 1, 2, 3, 4. So you can be geometrically meticulous, like I was, seemingly overly complex. And then when you take the derivative, what you notice is things like this and things like these 3, which actually so these 3 are constrained to be 0. These 2 are constrained to be the same as the velocity of b. So SG dot is equal to minus 6/4. Minus meaning it's being drawn back to the left as this is being drawn to the right. So that's kind of the long way to do it, and maybe it's good to do it kind of meticulous like that, up here at least. Do this out and then identify some of the things about it. And I don't think that this is only 12:206, so there wasn't another question. You could ask the question, how far did it move after 6 seconds or 1 second or whatever. In this case, it's implied that the acceleration is 0. So if that's the case, the velocity remains fixed. And then, S is equal to S naught plus V naught T plus the acceleration T squared over 2. If it has no acceleration, constant velocity, then all you do is if you want to know how far it moved in 1 second, 6 meters, and that moved 1 second, it'd be 6/4 meters. So, because there is no acceleration, if the velocity remains fixed. So that's pretty much it. These problems are fairly simple. They just have a couple of things to them. I will go, okay, so you already have a set for Sunday. I will send everybody an email and tell, because I'm going to do the same thing in all the classes. I'll maybe
maybe tomorrow morning, I'll send you an email that explains it all, that just says, in lieu of what we're doing, instead of you doing 2 assignments, one timed and one not, I'm just gonna dump it all into a homework. And so you won't have to deal with the other stuff. So the answer to the question is no, there's no test on Friday. Yeah,
Will that collapse the quiz category of the grade and homework?
right, yeah. So I mean, I'll just call it, I don't know, quiz homework, I don't know what it'll be. So whatever those 2 together were, I'll just add those 2 together, and that's what the remainder will be.